Swayam Prabha. Digital India. Educated India.
Okay, so last time we basically introduced a new concept which is called entropy, and we saw that it naturally emerges out of the formulation of reversible Carnot engine, right. So basically last time we defined the thermodynamic definition of entropy, thermodynamic definition of entropy, and it turned out this is the heat divided by the temperature, right. And we got excited about it because we realized that in a Carnot cycle the ratio of heat exchange divided by the temperature also remains a conserved quantity over a complete reversible cycle, right. And we also looked at the other fact that another thermodynamic quantity, for example internal energy that also remains conserved, right. So this implies, so we saw that if since this is also conserved, this ratio of heat by temperature is also a thermodynamic variable, right, it is a state function. Okay, so and we realize that this must be something very useful to basically consider in all the thermodynamic processes, right. And like I said, we saw over a reversible Carnot cycle, the total change in entropy over a complete cycle. So if you sum up all the heat exchanges divided by the temperatures of those particular processes, for example here I can run over an isothermal process, then an adiabatic process, then another isothermal process and another adiabatic process, but eventually essentially over a complete cycle. So over a cycle, and we saw that this is 0, right. So that means it is a conserved quantity, all right. And also later on we also looked we also saw that this is an important quantity because this basically turns out it tells us the direction in which all the thermodynamic processes are evolving. Okay. So other thing, towards the end of the last class we also discussed about principle of increase in entropy or increasing entropy, right. So basically we just thought that, say we have a basically the complete universe, right. So this is the universe, okay, and you have a certain process which is going on inside the universe in such a way that so it is a cyclic process, but process that happens from 1 to 2 happens irreversibly, but when it comes back it happens reversibly, right. So this is irreversible, this is reversible, right. And we saw using the Clausius inequality that S2 minus S1 in this case has to be greater than or equal to the integral of heat exchange over the irreversible cycle divided by the temperature, and this integral is evaluated from state 1 to state 2, right. And since, and this is again like an assumption, or you call it an basically an experimental observation, since first law of thermodynamics is true, that must imply that our universe is a isolated system, right. It does not exchange heat with the with anything else, right. All we know is universe, right. There is nothing outside the universe, and this universe somehow is like since it is isolated, there is no heat exchange, right. So any process which is happening inside the universe, that must be accompanied by dq equal to 0, right. So since universe is isolated, universe is isolated system. So, dq irreversible has to be 0, which implies S2 minus S1 has to be greater than it should be greater than this thing, greater than 0 if the process is irreversible, right. If anything that goes on inside the universe which is irreversible, for example, coffee and milk, if I mix them, if I add coffee into the milk, they mix and they form a like very homogeneous state, and that process is an irreversible process because we never see coffee and milk separating, right. And in that case the entropy always increases. Okay. So, whenever we have any irreversible process, the entropy has to increase. And more generally we can also say that S2 minus S1 is either greater than or equal to 0, and equal to 0 is for the cases which are reversible, like we saw in a Carnot cycle, right. So, therefore, in the end we concluded, that from first law what we learn about the universe. So, from first law the useful thing that we can say about the universe from first law is that the total energy of the universe is conserved. Okay, it does not change, it remains constant. And the second statement and from second law we can say that the change in entropy of the universe in any process is either greater than or equal to 0. Okay. It can never be less than 0. So, it is equal to 0 for processes that are at equilibrium and that are reversible, but if you have irreversible processes, the entropy always increases. Okay. So, I hope that concept was clear. All right. So, what we are going to do today is we are going to take a slight change in topic essentially, right. So, we are going to put some hints of statistical physics into this problem, right. So, even though we have explained entropy as the ratio of heat by temperature, it does not really give us any physical insight to what this quantity actually means. Okay. And that is where statistical physics, the concept of statistical mechanics, they come into importance. Okay. So, let us and I will basically explain the statistical meaning of entropy right now, and we will again go back to thermodynamics, all right, and we will formally come into this this part of the course later once we finish the thermodynamics, all right. But at this point it is actually, I think it is important to understand what entropy actually means, right. Okay. So, basically next thing is statistical definition of entropy. Okay. So, how do we understand this entropy, right? What is the origin of this this concept? All right. So, to understand this we have to explain, we have to define actually two more terms, right. So, one is microstate and the other is macrostate. So, what do we mean by that? Okay. So, again, so let us imagine that we have a system, all right. So, we have a system which consists of many gas molecules for example, right. And if I take a snapshot, right, what am I going to observe about the system? I am going to observe the position coordinates of any particular molecule and its momentum in 3 dimensions, right. And I am going to get that information for all 10 raised to the power 23 gas molecules, right, and that information at that point is a microstate, all right. So, maybe I can define. So, microstate is basically, microstate is a set of instantaneous R and P of all gas molecules. Okay. So, essentially Ri and Pi, where I runs from 1 to 10 raised to all the gas molecules 10 raised to power 23, all right. So, this is like a microstate, right. And what is a macrostate? So, this is basically, if you remember, this is what we were kind of interested in in kinetic theory, right, when we were formulating the kinetic theory. But when we started the thermodynamics, we said that we are just completely going to ignore all these microscopic details, right, and we were only interested in macroscopic thermodynamic variables. For example, okay, so the next thing is macrostate, and macrostate is thermodynamic variables like temperature, pressure, internal energy and so on, right. So macrostate is the consequence of what all the individual molecules are giving rise to at any particular time, right. For example, at any particular time all the molecules have positions Ri and momenta Pi, and it is giving rise to certain pressure at that particular moment and certain temperature at that particular moment, right. And you can already imagine that to get the temperature of this room to be exactly equal to 25 degrees Celsius, it does not matter whether molecule number 1 is moving with certain velocity or molecule number 2 is moving with certain velocity. What I mean is I can always exchange their velocity magnitudes between each other, but the temperature of the room will not change, right. Similarly, I can switch the positions of these two molecules between each other, the temperature of the room will not change. Similarly, the pressure of the room will not change, and this is exactly what we observe with the thermodynamic system, right, where we have billions upon billions particles or molecules, right. So that no matter what happens, once it is at equilibrium, the pressure and temperature of this system does not change, even though underlying reality is that the molecules are always exchanging positions, momenta and so on between each other, right. So what I mean is there can be multiple microstates corresponding to a macrostate. Okay. So a macrostate can have many microstates which give rise to that particular macrostate, like thermodynamic variable. All right. So I can give you another example if this is not clear. I will give you a very silly kind of example. So say we have a pool of mugs, right. So there are many cups which are kept aside, and half of the cups have milk in them and half of the cups have coffee in them, right. And I ask you to, and they are all randomly placed, right, and I ask you to lift one coffee mug and one milk mug and mix them together, right. So and you can imagine, so okay, so basically what I am saying is, so a cup, let me draw it, a cup can either have a milk or coffee, okay, and we do not know which mug has what, right, and I ask you to randomly pick two mugs, two cups, right. So what can happen is, let's do this thought experiment. So there are various scenarios which are possible, right. So either you can pick a cup which has milk, so cup number 1 has milk, cup number 2 also has milk, right, and if you mix them, so let me mix, or let me write cup 1 plus cup 2, right. So cup 1 plus cup 2, in which case this will also be okay. So since milk is white, so outcome will be white, right. So what will be the color? So let me write color. So the color of this mixture will be white, right, very simple. If you mix milk with milk, it will remain milk, right. But if you pick the cup number 1 has coffee and cup number 2 has milk, then what will you see is, you will see some light brown color, right. So light brown. But if your cup number 1 is milk and cup number 2 is coffee, you will again see light brown color if you mix them. And if your cup number 1 has coffee, cup number 2 also is coffee, then you will see brown color. Okay. So what I am saying is, corresponding to every microstate, right. Now what is the equivalent of microstate in this case? That is the state of that is the element which is present in the cup, whether it is coffee or whether it is milk, right. But when you mix them together, when you make a system out of it, you can only measure a thermodynamic variable, for example color, right. So, all you can observe is color, right, and it does not matter whether you mix cup number 1 has coffee milk and cup number 1 has coffee, cup number 2 has milk, or vice versa, you will always see a light brown color, right. So, therefore, in this case the macro state is equivalent to the color of mixture, right. And what is the microstate? So, microstate is what is cup 1 and cup 2, right, whether it is milk or coffee. So, the microstates in this problem can be MM, CM, MC and CC, right, but the macrostate is the color. And now you can see that there are two microstates corresponding to a single macrostate. Say my macrostate is light brown color, right. So, there are two possibilities to get that, either cup 1 has coffee milk, cup 2 has milk, or cup 1 has milk and cup 2 has coffee, all right. So, this is how you can try to understand this concept of microstate and macrostate, all right. And you can see that right now I just took example of 2 cups, right. So, now if you have many cups, right, you can see that there can be many microstates corresponding to single macrostate, right. So, I hope that thing is clear. Okay. So, now I will basically extend this analogy into a more mathematical formulation, all right. So, basically what I will say is, so let us say we have two systems, right. We have two systems and okay. So, say we have system 1. So, this is system 1, this is system 2. This system is kept at temperature T1, this is kept at temperature T2, and correspondingly its total internal energy is E1 and its internal energy is E2, right. So, this is T2 E2, okay. And say we have insulated them, right. So, these systems are like isolated and these systems are also isolated, right. They are not really exchanging any heat between each other, all right. So, like I said, corresponding to this temperature T1 or internal energy E1, there are say sigma 1 which is a function of E1 number of microstates, right. So, what I am saying is, if the kinetic energy of gas molecules in this room is certain thing, that certain number, there are certain number of microstates corresponding to that value of total kinetic energy, right. Now, if I change the temperature of this room, there will be okay. So, say I increase the temperature of this room, right. So, the distribution of the velocities will shift, like if you remember from kinetic theory, the Maxwell distribution shift rightwards, right, and there are greater and greater number of speeds and positions which these molecules can acquire. So, this number of microstates is a function of the thermodynamic variable that we are interested in, right. And similarly, the number of microstates in state number 2 is omega 2, which is also a function of E2, right. So, what I am saying is, omega 1 E1 and omega 2 E2 is number of microstates and E1 and E2 are the macrostates, all right. And let us say what we do is, so after some time, so we basically replace this wall with a conducting wall, right. So, say we replace this wall with a conducting wall. So, the overall this system remains isolated, but now this is a conducting wall. So, what will happen is the molecules will start exchanging heat between each other and this system will tend to another equilibrium state, right. So, we started with the state where the temperature on the left first system was T1 and the second system was T2, and very naturally you can very easily check that if we let this wall to be a conducting wall, there will be a new equilibrium state where the temperatures of this, so the temperature of both these system will be equal to each other, and that will be the equilibrium state, all right. But what happens to the microstates, right? So, after we remove isolation or insulation, so what will happen is, what will be the total number of microstates of this entire system, right? So, that will be, so total number of microstates. So, that will become omega 1 times E1 multiplied by omega 2 times E2, right. So, they get multiplied, and why is that? Because corresponding to every microstate on the first system, there are omega 2 number of microstates on the second system, right, and therefore, it gets multiplied, all right. Now, what is the condition? Okay. So, in this, so like I said, the condition of, from thermodynamics we know that the equilibrium is established when the temperatures become constant. But what happens to the microstates, right? And as you can imagine, if, okay, so let me go back to this coffee and coffee and milk analogy. So, if I ask you to pick two cups, so it's more likely to end up with a light brown color than to end up with either brown color or white color, because there are more number of possibilities which give rise to this macrostate, right. So, for example, if I rather than picking only 2 cups, I pick 100 cups, right. In order to get a brown color, you have to pick all the 100 cups which are just coffee, and you can see it's a very unlikely event, right. And you can see, you can already imagine, if you are picking 100 cups, the most likely state is that you are picking 50 coffee mugs, 50 coffee cups and 50 milk cups, right. That is the most likely state, right. So, therefore, the again, like this comes from the from our daily observation, right. So, this is how this universe operates. This is the law of large numbers and probabilities, right. The thing that is most likely to, which has the highest number of likelihoods, right, that is the one which happens most likely, right. So, therefore, I can say that okay, so the question that we are posing to ourselves is, what is the condition of thermodynamic equilibrium, okay. And like I said, that will be where you have maximum number of microstates, right. But there are certain important assumptions that go into this statement, right. So, assumptions. So, there are certain assumptions that underpin this statement, that the thermodynamic state corresponds to the highest number of microstates, which is the following: that each microstate is equally likely, okay. So, it is like saying it is equal, so the probability that I pick a coffee mug, so say, okay, so say there are like two coffee cups, right. So, the probability of picking coffee cup 1 with the cup 1 with coffee and cup 2 with milk is equal to the probability of picking cup 1 which contains milk and cup 2 which also contains milk, right. So, all these possibilities have equal probability, all right. So, that is the first assumption. The second assumption is that, now since remember we are dealing with a thermodynamic system, right, and it is evolving as a function of time, right. So, we are assuming that microstates change or microstates keep changing with time, okay. So, what that means is, if I am observing a container containing gas molecules, the positions and momenta of these gas molecules, they are always changing with respect to each other, right. So, it is not a snapshot that we are looking at, we are basically observing this system for a very long time, in which case all the microstates keep changing between each other, all right. And the third assumption is basically at t going to infinity, if we wait for a very long time, all the microstates are explored. Okay. So, system is able to explore all the possible microstates that actually are possible in that thermodynamic system. All right. Now, like I said before, on the grounds of concept of probability, the system will end up into a macro state which corresponds to the maximum number of microstates, right, a highest number of microstates. So, basically what I am saying is, in equilibrium, this quantity which is omega 1, which is function of E1, times omega 2, which is function of E2, is maximum. Okay. So, that will be the macro state of the system where it will most likely to be present. All right. So, in other words, we can say that the derivative of this quantity with respect to energy, say E1, or you can take E2 as well, is 0, right. So, omega 1 E1 omega 2 E2 equal to 0, and this is in equilibrium. So, equilibrium is when this quantity does not change anymore, right. So, the total number of microstate achieves a maximum number. All right. So, if we simplify this, so we can check that this is omega 2 d omega 1 by dE1 plus omega 1 times d omega 2 by dE2 times dE2 divided by dE1, and this is equal to 0. All right. And remember, both these systems together also remain insulated, right. So, what I mean is, the sum of E1 and E2 does not change, right, because it is not really exchanging heat with surroundings. All right. Also, E1 plus E2 remains constant, which simply implies that dE1 plus dE2 equal to 0, or in other words, I can see dE2 by dE1 is minus 1. All right. And if I plug that value here, we can see that omega 2 times d omega 1 by dE1 equals omega 1 times d omega 2 by dE2, or in other words, I can write it in a slightly better way. So, 1 by omega 1 d omega 1 by dE1 is equal to 1 by omega 2. Okay. So, in equilibrium, this is the condition. All right. And this I can rewrite as the derivative d by dE1 of log of omega 1 equals d by dE2 of log of omega 2, right. So, this is the condition for equilibrium, right. So, remember, I already told you, like when we let this system exchange heat with each other, the equilibrium is established when the temperature T1 becomes equal to temperature T2, right. Also, the other condition of equilibrium is T1 equals T2. So, therefore, this quantity, which looks like the derivative of log of number of microstates with respect to total energy, has to be related to temperature, right. So, what I am saying is, so therefore, this d by dE of log of omega has to be proportional to has to be related to temperature, right. So, let us say this is 1 divided by T, okay, and this is purely by definition, right. So, this is definition, okay, and it turns out we can actually remove this proportionality sign and introduce this constant, which is the Boltzmann constant Kb, and this equation basically stands for the statistical definition of so this is the statistical definition of temperature. Okay, so this is an important relation. So this is how we define temperature from statistical physics point of view. All right. So our next aim basically is to express entropy in terms of this newly defined quantity, which is microstates. Okay. So let us do that. So let us revisit the first law. Okay. So first law. So what is the statement of first law? That is, the change in internal energy is equal to the work done on the system or by the system and heat exchanged by to heat given to the system or heat released from the system. All right. And also since we defined entropy, okay, so since entropy is the ratio of heat and temperature, right. So we can write this dq is nothing but this is T times ds, right. So this is the definition of heat in terms of entropy, and also we already know that the work done is equal to negative of P dV. Okay. So therefore we can rewrite the first law in this way. So du equals TdS minus P dV. Okay. And this is basically another statement of first law expressed in terms of entropy. Okay. Now you can see that in this case the internal energy function is actually a function of two variables, two independent variables, which is entropy and volume. So therefore we can write its differential as follows. So this is del u divided by del s. So partial derivative of u with respect to s at constant volume times ds plus del u by del v at constant entropy times dV. Okay. So therefore if we compare these two equations, right, if we compare these two equations, we can see that temperature is partial derivative of internal energy with respect to entropy at constant volume, and pressure is negative of partial derivative of internal energy with respect to volume at constant entropy. Okay. So, but more useful quantity here is the temperature, which is del u by del s at constant V, and also from this equation. Okay. So so what I am saying is, so we just saw that the temperature equals del u by del s at constant volume, and also from this equation, okay, or I can express this as follows, or the inverse of temperature is del s by del u at constant volume. All right. But also from the statistical definition of temperature, what is inverse T? That is Kb times d by dE of log omega. Also 1 by T equals Kb times d by dE of log omega. Okay. And now I want to basically highlight that that the quantity E and U, they are not really different, right. So they both express the internal energy of the system. So E is equal to is equivalent to U, and both are internal energies. Okay. So therefore we can equate them. So Kb times d by dE of log omega equals del s by del E. I am just replacing U with E here at constant volume. All right. And you can see that these differentials, they cancel out, and we can express our entropy. Okay. And if we integrate it out, so we get entropy, which is Kb times, so this d of log omega just gets converted into log omega plus some constant c. All right. And this is the definition of entropy expressed now in terms of the number of microstates in the system, and this is some arbitrary constant which you can say that some entropy which is independent of this omega, and it turns out we can always set it to 0. Okay. So set to 0, and which leaves us with a very important equation, which is the entropy S is equal to Kb times log of omega, okay, and this is known as Boltzmann equation. Okay. So, this is entropy expressed in terms of number of microstates. Okay. So, therefore, entropy is basically just a measure of how many possible microstates are there in a particular macrostate. Okay. So, this is just a measure of that. Okay. All right. So, so the next thing that we can quickly talk about is basically another concept which is called Gibbs expression of entropy. Okay. Okay. So, Gibbs expression for entropy. Okay. So, we just saw that we can express this entropy S as Kb Boltzmann constant times log of the number of microstates. Okay. Now, I want you to think about it, right. So, when we say number of microstates, and remember I also assigned microstates with instantaneous position and momenta of all the gas molecules. Okay. And let me take the example of gas molecule, right. So, gas molecule can move anywhere between 0 to any kind of velocity, say 1 centimeter per second for example, right. And if I ask you how many number of values are there, how many possibilities or how many numbers are possible between two real numbers, that is a very large infinite quantity, right. So, there are infinite number of real numbers between any two real numbers, right. So, therefore, it turns out this omega in classical limit is a very, it is basically infinite, right. It is difficult to make sense of it, at least physically, right. So, because gas molecules can move with all these all possible velocities. So, how do we make sense of it? Okay. So, so what we do is we assume that no matter what happens, let us say there are still finite number of microstates in the system, right. So, let us assume there are finite number of microstates. It turns out, as we will see when we get into into statistical mechanics, that the quantum mechanics come into our rescue. Okay. Due to uncertainty principle, we can't really pinpoint the position and momenta of a gas molecule with pinpoint accuracy. So, there is always a discreteness in these, and the omega ends up to be a finite number, albeit very large number, but still a finite number. Okay. But still, let us assume this omega is this number of microstates is a finite number, and let us call it n in this case. So, so basically they mean the same thing. So, number of microstates is n. Okay. Okay. And this is microstates corresponding to all the possible macrostates in the system. So, corresponding to all possible macrostates. Okay. So, let us call that number to be n. Okay. And also say okay. So, and say there are certain number of macrostates in the system. Okay. So, corresponding to each macrostate there are ni microstates. So, that means say for macrostate number 1 there are n1 number of microstates, for macrostate number 2 there are n2 number of microstates, and so on. Okay. And there can be large number of macrostates as well. All right. And you can see that the sum of this ni over all the microstates. So, all the macrostates where I runs for over all macrostates. So, basically is equal to n. Okay. And the sum is over all macrostates. Okay. So, all the microstates present in all the macrostates, they have to sum up to n, which is the total number of possible microstates. Okay. So, therefore, the probability to exist in a particular macrostate. So, probability to exist in ith macrostate, that simply becomes Pi equals Ni divided by n. Okay. And from this Gibbs expression for entropy, we know the total entropy of this system considering all the possible microstates is as follows. So, total entropy, which is S total, is Kb times log of n. Okay. But we know that the contribution to this total entropy comes from two terms, right. So, this S total is basically equal to S plus S micro, and where S is entropy due to different macrostates, and S micro is entropy due to those microstates in that particular macrostate, right. Entropy due to microstates in a particular macrostate. Okay. So, therefore, since there are Ni number of microstates in ith macrostate, so the entropy contribution okay. So, entropy of ith macrostate is only due to the number of microstates in that particular macrostate, and that is Si, right. So, that is Si, which is Kb times log of Ni. Okay. And okay. So, and this is the entropy of one macrostate, but what will be the average entropy of a macrostate? Okay. So, that will be okay. So, okay. So, this is the entropy of ith macrostate, which has some number of microstates. So, what will be the average entropy contribution to due to these microstates present in a particular macrostate? So, that will be, so let us call this S micro, the entropy contribution due to microstates in a particular macrostate, that will be the average over this quantity, right. So, the average of Si, where averaging is done over all possible macrostates, right. And by definition, this is just equal to sum I Pi dot Si, right, where Pi is the probability to stay in that particular macrostate, right. So, the probability to stay in that particular macrostate multiplied by the entropy of that macrostate and sum over all the states, that gives you the contribution of microstates while they are inside a particular macrostate. Okay. So, therefore, the total entropy so this total entropy, which was sum of S plus S micro, right. So, therefore, the S becomes S total minus S micro, and we can now replace that here. So, that becomes Kb times log n, right. So, remember, this is the total entropy, S total, right, which is Kb times log n minus this quantity Pi Si. Okay. And now I can replace this Pi Si, and what is Si? This is Kb times log Ni. So, this is Kb times log n minus Kb times summation over I Pi log of small n I, and let us call this equation number 1, and this is S, okay, and S is the entropy contribution due to these macro states. Okay. So, also since the quantity Pi is equal to Ni divided by N, right, this is the probability. Okay. So, this implies log Pi equals log Ni minus log N. Okay. And if we multiply both sides by Pi, so multiplying both sides by Pi, so we get Pi log Pi equals Pi log small ni minus Pi times log n. So, remember what we are after? We are after this quantity, which is sigma summation over Pi log Ni. Okay. So, next step naturally what we will do is we will take sum over I, right. So, okay, so summing over I, so this equation becomes Pi log, so log Pi equals Pi log Ni Ni minus Pi log n. Okay. And what is sigma Pi, right. So, since sigma, so this is basically equal to 1, right, the total probability to be in any macro state is 1. So, therefore, this sigma I Pi log Ni simply becomes sigma I Pi log Pi minus this sigma goes away. So, minus log n. Okay. So, now we are ready to substitute this quantity here. Okay. So, substituting in 1, okay, and we get, so we can write our S equals Kb log n. So, S becomes Kb log n minus Kb times I Pi log Pi minus sorry, this should be plus, this should be plus. So, this becomes minus, right. So, this goes on the other side and this becomes plus. So, minus Kb times log n, and you can see these two terms cancel out, and finally, we end up with the entropy of a particular macro state to be equal to minus Kb times sum over I times Pi log Pi, and this equation is basically the known as Gibbs expression for entropy. Okay. So, this is another way of defining the entropy of the system, considering the quantities like the probability to stay in a particular macro state and so on. Okay. And you can see that there is a negative sign which might sound confusing to begin with, right. As you know, entropy can never be negative, but remember there is a quantity called like log of Pi, and Pi's are probabilities which are always less than 1, right. So, therefore, log of Pi is itself a negative quantity. So, to counter that, this negative sign naturally arises here. Okay. And to end basically, okay. So basically what we have done is, so we in the last class we basically accidentally encountered a new thermodynamic variable which was entropy, and we saw that this is ratio of heat divided by the temperature, and we and that was kind of confusing because it didn't really tell us any physical meaning to that quantity. So, we kind of made a small switch to statistical mechanics, and we introduced the concepts of microstates and macrostates, and now we can like physically understand what is the origin of entropy, right. The origin of entropy is basically just the mathematics of large numbers, right. So it's just the probabilistic law. Okay. So it's more likely to end up in a state which has more possibilities. Okay. And it's very natural thing for us to think about. Okay. And going by that logic, we defined, or we derived very two important equations. One was the Boltzmann equation, which expresses entropy in terms of the total number of microstates that are present in the system, and another way of defining the same quantity, which is in terms of the probability to stay in a particular macro state. Okay. So we basically derived these two quantities. So towards the end we can just say a few things. Okay. So some important concepts about entropy. Okay. Some concepts. Okay, so basically, so some salient features. Okay. So salient features of entropy. Okay. So these are some features which we should like understand which are associated with this entropy, right. So you can already guess that this entropy is an extensive variable. Okay. So entropy is an extensive variable. Okay. Which means it scales with the system size, right. So if I have 10 molecules and if I have 20 molecules, 20 molecules will have more number of microstates because there are more number of positions and momenta associated with those molecules. So there are more number of microstates, so entropy scales accordingly, right. And also we saw in this class that the reason the entropy is maximized is okay. So since system tends to stay in a state with more number of microstates, okay, which is omega, right. So therefore when we saw that entropy is nothing but it's just proportional to that quantity omega here, right. So therefore it's natural to assume that the entropy associated with that also maximizes, right. Which implies maximizing entropy. And you can see there we are not really proving this statement, right. It is like asking why is it more, okay. So say if I give you number of cups which has so say there are 100 cups, and say there are cups which contain coffee and milk, and I ask you to pick 100 cups at random. The most likely event for that, if you pick 100 cups, the most likely outcome will be that 50 cups will have coffee and 50 cups will have milk. Okay. This is this just comes so naturally to us, right. So this is just mathematics, it is probabilities. Okay. And there is no proof of that, right. I can't really prove why that is the most likely outcome, right. But this is how the numbers work, right. This is the law of probabilities when we deal with large numbers. Okay. So there is so what I am trying to say is there is no so no proof of this. Okay. But this is law of probability, right, laws of probability. So nature of our universe is such that whichever state has higher multiplicity, more likelihood of happening, that happens, right. So this is in that sense it is a law of probability. Okay. And on the similar lines, okay, in the we can also say that the second law of thermodynamics, right. So second law of thermodynamics, which we saw basically told us that processes evolve only in the direction of increasing entropy, it's not really a fundamental law, right, and it is true only in a thermodynamic limit, is not fundamental in nature and is applicable to only to a large collection of particles. Okay. So this law takes importance only when we are dealing with large number of gas molecules. If I am only dealing with 3 molecules, I can't really define the concept of entropy because its origin is statistical in nature, right. We deal with averages and probabilities. Okay. Okay. So I think we can end here. So I'll see you in the next class. Thank you.